For as long as human beings have reflected on the nature of existence, one question has haunted our thoughts. What is reality? Is what we see, touch, and experience the true nature of the world, or is there something deeper, something hidden beneath the surface, connecting everything in ways we can't always perceive? This question has inspired entire philosophical traditions, spiritual teachings, and religious beliefs. Across cultures and epochs, there's a recurring idea that life is interconnected, that nothing exists in isolation, and that behind the veil of appearances, there's a deeper unity that binds all things together. In ancient Greece, Plato spoke of the forms, ideal, perfect realities that exist beyond the world of everyday experience. To Plato, what we see are mere shadows of a deeper truth, a fragmented reflection of something more fundamental. In the East, the spiritual concept of oneness, or non-duality, suggests that the separation we experience between self and other, mind and matter, is an illusion. From the Hindu notion of Brahman, the infinite essence behind the material world, to the Buddhist idea of interdependence, where all things arise and exist only through their relationships to others, the message is clear. Reality is profoundly interconnected. Religious traditions, too, have long embraced this idea, whether it's the concept of the divine unity in Sufism, the holistic balance of the Tao in Taoism, or the idea that all things are one in mystical Christian thought. There is a deep, almost intuitive sense in humanity's collective wisdom that the universe is not made up of isolated, separate entities, but rather that we are all part of a vast, interwoven tapestry. And yet, in our everyday lives, we don't often experience this unity. We see distinct objects separated by space. We live in our own minds, separated from others by the boundaries of our bodies and our individual perspectives. So, how do we reconcile this ancient, pervasive intuition of connectedness with the fragmented world we encounter? In the 20th century, the physicist David Bohm took this ancient question of connectedness and brought it into the realm of science. He wasn't satisfied with the prevailing view of reality offered by classical physics, or even the emerging counterintuitive world of quantum mechanics. For Bohm, both approaches fell short of explaining how the universe could be both fragmented and unified at the same time. But here's the interesting part. Bohm's journey toward this question wasn't purely scientific. He was deeply philosophical, even spiritual in his approach to physics. He was searching for a framework that could explain the paradoxes of quantum theory, while also accounting for the deeper interconnected nature of reality that so many traditions had hinted at for millennia. Bohm believed that the way we typically view reality as a series of separate, isolated parts was, in fact, an illusion. He proposed that there is an implicate order, a hidden realm in which everything is interconnected, and from which the reality we perceive, what he called the explicate order, unfolds. But rather than seeing this connectedness through the lens of spiritual mysticism or ancient metaphysics, Bohm attempted to ground it in the world of quantum physics. He believed that the strange behavior of subatomic particles, particles that seem to communicate across vast distances and act in ways that defy our classical understanding, was evidence of a deeper, hidden order. But here's where we start to ask the difficult questions. Can Bohm's theory, with its roots in quantum mechanics, really offer a clear explanation of the connectedness that so many philosophical and spiritual traditions point to? Or is there something missing? Is this implicate order he describes truly the key to understanding the universe? Or does his attempt to ground it in the quantum realm limit its potential? Today, I want to explore these questions. We'll dive into Bohm's theory of implicate and explicate orders, examine its basis in quantum mechanics, and then consider an alternative, a more holistic interpretation that may bring us closer to understanding the true nature of interconnectedness. So, let's begin by unpacking Bohm's theory. What exactly did he mean by these hidden connections that supposedly shape the world we experience? Bohm's work grew out of the strange, counterintuitive discoveries of quantum mechanics, the branch of physics that deals with particles at the smallest scales of existence. At this quantum level, the world behaves in ways that seem completely at odds with our everyday experiences. Electrons can behave like both particles and waves depending on how we observe them. Particles that are separated by vast distances can somehow influence each other instantly, a phenomenon known as non-locality. These strange, seemingly paradoxical behaviors led many physicists to embrace the Copenhagen interpretation, which suggests that at its core, reality is probabilistic. In other words, particles don't have definite properties until we observe them. But Bohm was unsatisfied with this explanation. He couldn't accept that reality was simply a series of probabilities waiting for an observer to collapse them into definite outcomes. He believed there had to be something deeper going on, something that could explain the hidden connections between particles that seem to communicate across vast distances. To address this, Bohm proposed the existence of the implicate order. In the implicate order, Bohm argued, everything is fundamentally interconnected and enfolded into everything else. The explicate order, the world we see and experience, is simply an unfolding of this deeper order. Think of it like a hologram. In a hologram, every part contains the whole image. In Bohm's view, every part of the universe contains information about the whole, and the separateness we perceive is merely a surface level appearance. The question Bohm was trying to answer was this: how do we explain the deep non-local connections between particles that we see in quantum mechanics? His answer was the implicate order, a reality where separateness doesn't truly exist and where everything is connected at a deeper level. Now, this theory sounds incredibly appealing. It suggests that beneath the fragmented world we experience, there's a more unified, holistic reality. But Bohm grounded his theory in quantum mechanics, specifically in the behavior of subatomic particles. And here's where we need to ask some important questions. Can we really extend the strange behavior of particles at the quantum level to explain the larger macroscopic world we live in? Does Bohm's theory, rooted in the abstract and often perplexing realm of quantum mechanics, actually give us a clear picture of interconnectedness? Or, by focusing on the quantum scale, is Bohm missing the larger systemic forces that might provide a more grounded understanding of how the universe is connected? These are the questions we'll explore together. I want to take you on a journey beyond the limits of Bohm's quantum interpretation and suggest an alternative, one that grounds the idea of interconnectedness, not in the subatomic world, but in the larger holistic systems that shape our everyday reality? Could it be that the real wave functions, the real connections aren't hiding in the strange probabilistic world of quantum physics, but are found in the macroscopic measurable systems all around us? And if that's the case, what does it mean for our understanding of reality? With these questions in mind, let's dive deeper into Bohm's theory, examine its strengths and limitations, and consider a new perspective that may bring us closer to the truth of the interconnected universe. So, let's begin by taking a closer look at Bohm's vision of reality. To understand his theory, we first need to dive into the world of quantum mechanics, which is where his ideas are rooted. Now, quantum mechanics is notorious for being one of the most successful, yet philosophically troubling fields of physics. It gives us highly accurate predictions for the behavior of particles at the smallest scales, but it also defies much of what we think we know about the nature of reality. At the quantum level, particles like electrons and photons behave in strange, almost paradoxical ways. They don't seem to follow the neat rules of classical physics, the physics of Newton that we're familiar with. Instead, they act as if they can be in multiple places at once, or they can behave both as particles and as waves depending on how we observe them. And perhaps strangest of all, particles that are light years apart can influence each other instantaneously, as if distance doesn't matter, a phenomenon known as quantum entanglement. Most physicists, when faced with these strange quantum phenomena, follow the Copenhagen interpretation of quantum mechanics. This interpretation, championed by Niels Bohr and Werner Heisenberg in the 1920s, suggests that quantum systems don't have definite properties until they are measured or observed. Before you measure a particle, it exists in a state of superposition, meaning it occupies all possible states at once, as described by a mathematical function called the wave function. Once you measure it, the wave function collapses, and the particle takes on a definite position, speed, or spin. In the Copenhagen view, reality is fundamentally probabilistic. We can never know with certainty where a particle is or what it's doing. We can only predict the likelihood of certain outcomes. And here's the kicker. Observation itself seems to play a crucial role. Reality, in a sense, is defined by our measurement of it. Without observation, the world exists only in a cloud of probabilities. And it's only when we step in and take a look that reality solidifies. For many, this interpretation has worked wonders in terms of making predictions. It's the foundation of modern quantum mechanics and has been verified through countless experiments. But this probabilistic, observer-dependent reality has always troubled some scientists, including Bohm. Is this really how the universe works? Are we supposed to believe that reality doesn't exist in any definite way until we observe it? Bohm thought there had to be a deeper explanation, something that accounted for the strange behavior of particles, but didn't hinge on the role of the observer or the randomness of quantum probabilities. David Bohm wasn't satisfied with this view of reality as a mere collection of probabilities waiting for an observer to come along. He wanted to reintroduce a sense of determinism, the idea that there are underlying definite states governing the behavior of particles, whether we observe them or not. And so he proposed something radical, the existence of a hidden order, a deeper layer of reality that we don't directly perceive, but that holds everything together. He called this the implicate order. In Bohm's view, the implicate order is a realm where everything is fundamentally interconnected. Particles don't just exist as isolated points in space. Instead, they are enfolded into a larger whole. The world we perceive, what Bohm called the explicate order, is merely an unfolding, a projection of this deeper implicate order. To understand this, imagine a hologram. In a hologram, every part of the image contains information about the entire image. You can cut a hologram into smaller pieces, and each piece will still contain the entire original picture, albeit in lower resolution. For Bohm, reality works in much the same way. The world we see is a fragmented, unfolded version of the implicate order, where every part is connected to the whole. This idea was Bohm's attempt to explain the non-locality of quantum mechanics, the fact that particles can influence each other across vast distances instantly. In his implicate order, particles are not truly separate. They are part of the same interconnected field, enfolded into the larger whole. This hidden reality doesn't obey the ordinary rules of space and time. In the implicate order, everything is interconnected in a way that transcends our usual understanding of locality and causality. To give his implicate order a solid foundation in physics, Bohm developed an alternative to the Copenhagen interpretation called the pilot wave theory, or what is sometimes called Bohmian mechanics. Unlike the Copenhagen interpretation, which treats the wave function as a mathematical tool for predicting probabilities, Bohm's theory treats the wave function as a real physical entity. It's not just an abstract representation of possible outcomes. It's a wave that actually exists and guides the motion of particles. Here's how it works. In Bohm's view, particles always have definite positions and velocities, but their motion is guided by the pilot wave, a kind of hidden influence that tells the particle where to go. This pilot wave is akin to a ripple on the surface of a pond, where the particle is like a small boat being carried along by the waves. The wave function still obeys the Schrödinger equation, the core equation of quantum mechanics, but instead of collapsing when observed, the wave function continues to evolve, always guiding the particle along its path. This gives Bohm's theory a deterministic flavor. If you know the starting conditions, the initial position of the particle, and the state of the pilot wave, you can predict exactly where the particle will go. Bohm's theory elegantly solves some of the paradoxes of quantum mechanics. In his framework, particles are always real objects with well-defined properties, regardless of whether or not they are being observed. There's no need for the wave function to collapse, and reality isn't dependent on the act of observation. The pilot wave connects everything, even particles that are light years apart, explaining the non-locality we observe in quantum entanglement. Bohmian mechanics, in essence, offers a picture of the universe as a deeply interconnected, deterministic system, a world where everything influences everything else in subtle, unseen ways. Now, how do we get from this deeper, hidden implicate order to the world we see and experience every day? The Explicate Order. Bohm believed that the universe is in a constant state of unfolding and enfolding. The implicate order is constantly enfolding new information into itself, while at the same time, the explicate order is unfolding out of the implicate. This process is dynamic and ongoing, an ever-changing dance, where the hidden potentialities of the implicate order manifest in the visible world, only to be enfolded back again. For Bohm, this was a way of explaining not just quantum phenomena, but the nature of reality itself. Everything we see in the explicate order, the everyday world of objects and events, is the result of a deeper process. When you observe a particle or measure a physical property, you're seeing only one aspect of the whole, one fragment of the larger, interconnected, implicate order. The particle is not isolated. It is part of a vast web of connections that stretches across the universe, enfolded in the implicate order. This unfolding is also not confined to space and time as we understand them. Bohm's implicate order is timeless and spaceless, a deeper realm where all things are connected beyond the limits of ordinary physics. In this sense, Bohm's theory resonates with the spiritual and philosophical traditions we discussed earlier, which often speak of a deeper, hidden unity behind the apparent separateness of the world. Now, this all sounds very compelling. It offers a coherent, elegant explanation for some of the strangest phenomena in quantum mechanics, and it paints a picture of reality that aligns with ancient ideas of interconnectedness. But Bohm's theory also raises some difficult questions. Can we really extend quantum mechanics, a theory that works so well for predicting the behavior of particles, to explain the whole of reality? Does this hidden implicate order actually exist, or is it just another layer of abstraction, a way of trying to resolve the puzzles of quantum mechanics without providing new testable insights? And most importantly, by grounding this theory in the quantum realm, is Bohm missing the larger systems that govern the world we experience, the macroscopic systems that might offer a more direct and measurable way of understanding interconnectedness? These are the questions that lead us to our next step. While Bohm's theory offers a fascinating vision of the universe as interconnected and unified, we have to ask whether his focus on quantum mechanics limits our ability to see the bigger picture. Could it be that the real connections, the real implicate order, are not found in the abstract world of particles and pilot waves, but in the larger, holistic systems that shape the everyday world around us? That's what we'll explore next, as we move from Bohm's quantum theory to a broader, more grounded understanding of how interconnectedness works at the macroscopic level, where we can observe and measure it directly. So, we've taken a good look at David Bohm's theory of the implicate and explicate orders and how he grounded this idea in the strange world of quantum mechanics. He proposed that what we observe in everyday life, the explicate order, emerges from a deeper, hidden layer of reality where everything is interconnected, called the implicate order. And while his theory offers an elegant, almost spiritual vision of a connected universe, there are limitations, serious ones, that arise from tying this concept too closely to quantum mechanics. Now, before we go further, let's pause and ask, what exactly are these limitations and why do they matter? Because Bohm's work has inspired many people, but at the same time, the more we dive into his ideas, the more we realize that anchoring the concept of interconnectedness in quantum mechanics introduces some challenges, and perhaps more importantly, it blinds us to other, more practical ways of seeing how interconnectedness plays out in the real world, ways that are measurable, observable, and grounded in larger systems. Let's begin by examining Bohm's reliance on quantum mechanics. As we discussed earlier, Quantum mechanics deals with particles at the smallest scales, subatomic particles like electrons, quarks, and photons. And yes, the behavior of these particles is mind-bending. They don't behave like the physical objects we encounter in our daily lives. They don't have definite positions or velocities until we measure them. They can be in a superposition of multiple states at once, and they can even communicate across vast distances instantaneously, a phenomenon known as quantum non-locality. Bohm's genius was in trying to explain these bizarre behaviors with his idea of the implicate order. He wanted to move beyond the probabilistic interpretation of quantum mechanics and show that these particles, despite their apparent randomness, are actually connected through deeper forces we don't directly perceive. He used his pilot wave theory to suggest that particles have real deterministic paths, guided by a wave function that represents this deeper, hidden reality. But here's the issue. Quantum mechanics works incredibly well when we're dealing with systems on the microscopic scale. It predicts the behavior of particles with astonishing accuracy, but that's where it stays. These quantum effects, such as superposition or entanglement, become vanishingly small as we move to larger scales. Quantum mechanics is great for explaining the behavior of individual particles, but it struggles to explain larger, more complex systems, like the world we actually live in. When Bohm grounds his theory of the implicate order in quantum mechanics, he's trying to use a theory that works on the smallest of scales to explain the entirety of reality. And that's where we hit a wall. How do we scale up from the quantum world, where probabilities and wave functions dominate, to the macroscopic world, where we deal with things like chairs, trees, oceans, and entire ecosystems? Quantum mechanics can describe the behavior of a single electron, but it can't easily tell us about the behavior of a whole system, like the climate, or a galaxy, or even a living organism. And that's where Bohm's vision runs into trouble. By tying his theory of interconnectedness to quantum mechanics, he limits its application. He's focused on phenomena that occur at scale so small and under such specific conditions that they don't really help us understand the broader systems we interact with every day. The strange non-local behavior of quantum particles doesn't seem to scale up into the larger world. And that brings us to an important question. Is it possible that by focusing on the quantum level, Bohm missed the real observable connections that exist at larger macroscopic scales? This is where we need to shift our thinking. While Bohm's idea of a deeper interconnected order was ambitious, the reality is that we can find interconnectedness, real measurable connections, by looking at larger holistic systems, not just quantum particles. These systems exist all around us, and they operate under principles that we can observe and understand without diving into the complexities of subatomic particles. Let's take an example that many of us are familiar with. Temperature. Temperature is a property we all experience. It's something you can measure with a thermometer. But here's the thing. Temperature doesn't exist at the level of individual particles. You can't assign a temperature to a single atom. Instead, temperature is what we call an emergent property, a property that arises when we look at the collective behavior of many particles together. Temperature emerges when we consider how all the particles in a system are interacting, how fast they're moving, and how they're transferring energy. In other words, temperature is a macroscopic property, a feature that only becomes meaningful when we look at a larger system. And yet temperature is real, measurable, and it profoundly affects the behavior of everything from the weather to the human body. And temperature is just one example. There are many emergent properties in nature, things like pressure, fluid flow, or even the behavior of entire ecosystems that can only be understood by looking at the interactions between the parts of a system. These are holistic systems where the whole is greater than the sum of its parts, and the behavior of the system can't be reduced to the behavior of individual particles. The connections between the parts are what create the system's overall behavior, and these connections are non-local in the sense that changes in one part of the system can influence the entire system, often across large distances. Think about how weather systems work. A change in temperature or pressure in one part of the atmosphere can influence weather patterns hundreds or even thousands of miles away. Or consider gravitational fields, where the pull of a distant planet or star can affect the motion of objects across vast distances. These are examples of real, observable, non-local connections that operate on macroscopic scales, far beyond the realm of quantum mechanics. So, where does this leave us? Instead of trying to understand interconnectedness by diving into the abstract world of quantum mechanics, we can shift our focus to these larger systems that exhibit real, measurable connections between their parts. And here's where we introduce a new perspective on wave functions, not as abstract mathematical objects tied to the behavior of individual particles, but as system-level resonances that emerge from the interactions between different forces. Let's return to the idea of a wave, a stable, harmonic resonance. Waves don't just appear out of nowhere. To create a stable wave, you need three things: a force, an opposing force, and a bounding force that keeps everything in balance. Think of the ocean. Waves on the surface of the ocean are created by the wind of force, the resistance of the water, an opposing force, and gravity, which bounds and shapes the waves. This triad of forces keeps the system in balance, creating stable, predictable waves. This concept of forces interacting to maintain balance is something we see over and over in nature. And it's these triads of forces, force, opposing force, and bounding force that create the non-local connections between parts of a system. Just as gravity acts across space, these interactions allow distant parts of a system to influence each other, creating the stable patterns we observe in things like weather systems, ecosystems, and even the human body. These wave functions in our interpretation aren't confined to the quantum world. They're real physical phenomena that emerge from the interactions between forces in larger systems. And unlike the wave functions of quantum mechanics, which are abstract and probabilistic, these wave functions are measurable and observable in the macroscopic world. In essence, what we're proposing is a shift in perspective. Instead of looking to quantum mechanics for answers about the interconnectedness of reality, we should be looking at holistic systems, systems where emergent properties like temperature or pressure reveal the deeper connections between their parts. These systems operate on larger scales, and they offer real, testable examples of non-local connections. Bohm's vision was right in one important sense. There is an underlying order to reality where the parts of a system are connected in ways that aren't always immediately visible. But the mistake was in thinking that these connections are hidden in the quantum world, when in fact we can observe them at macroscopic scales all around us. Whether it's in the way ecosystems balance themselves, the way weather systems operate, or even the way gravitational fields influence objects across space, we can find the kind of interconnectedness that Bohm was looking for right here in the world we interact with every day. So where does this leave us? It leaves us with a new way of understanding reality, one that doesn't rely on abstract quantum mechanics, but instead focuses on the larger holistic systems that define our world. These systems show us that interconnectedness isn't some mystical property hidden away in the subatomic realm. It's a fundamental feature of the universe at all scales. As we continue to explore the nature of reality, perhaps the key isn't in diving deeper into the microscopic, but in stepping back and seeing the bigger picture. Bohm's vision may have been limited by its quantum foundation, but the idea of a unified, interconnected world lives on, and it's something we can observe, measure, and understand in the larger systems that shape our everyday lives. Now that we've explored the limitations of Bohm's quantum-based vision of reality and shifted our focus to larger holistic systems, it's time to bring everything together. We've seen how interconnectedness isn't confined to the strange, abstract world of subatomic particles, but instead can be found in the very fabric of the systems that make up the world we live in. But what does this all mean? And how does this new perspective on interconnectedness help us understand reality in a deeper, more practical way? Let's start by revisiting the core question that Bohm was trying to answer. How is it that everything seems separate, yet at some deeper level, everything is connected? Bohm's implicate order was his attempt to resolve this tension, a hidden realm of interconnectedness that gives rise to the fragmented world we experience. But by focusing too much on quantum mechanics, Bohm's explanation of this interconnectedness remained elusive, difficult to scale up, and impossible to observe directly. What we're proposing instead is a more accessible, more observable framework for understanding interconnectedness, one that's rooted in the dynamics of holistic systems. These systems are everywhere: ecosystems, weather patterns, biological organisms, and even entire galaxies. They demonstrate non-local connections, not through the behavior of individual particles, but through the complex interplay of forces that govern the behavior of the whole system. One of the key concepts here is emergence. Emergent properties are those that arise from the interactions of many components but can't be reduced to the behavior of any single part. Temperature, as we discussed earlier, is a perfect example. You can't understand the temperature of a gas by looking at a single molecule. It's only when you consider the collective behavior of all the molecules that temperature becomes meaningful. But it's not just temperature. Emergence plays a central role in understanding how complex systems work. Take consciousness, for example. Despite centuries of study, we still don't fully understand how the brain, an organ made up of billions of neurons firing in complex patterns, gives rise to conscious experience. Consciousness is an emergent property. It's not something you can pinpoint in any individual neuron or brain cell. It only becomes meaningful when we look at the whole system of the brain working together. This idea that the whole is more than the sum of its parts is crucial to understanding how interconnectedness works in nature. Systems behave in ways that can't be reduced to the sum of their individual components. This is why a reductionist approach, breaking things down into smaller and smaller parts, often fails to capture the richness of reality. The connections between the parts and the emergent properties that arise from these connections are what give systems their complexity and their power. So how do we explain these connections in a more concrete, measurable way? Let's return to the triad of forces we discussed earlier. In any stable system, whether it's a weather pattern, an ecosystem, or even a star, you have three forces at play. A driving force, the energy pushing the system in a particular direction, an opposing force, the resistance or counter energy, and a bounding force, which keeps the system within certain limits. These forces interact to create homeostasis, a balance that allows the system to maintain stability over time. It's this triadic interaction that creates the wave-like resonances we see in real systems, waves that reflect the interconnectedness of the parts. These resonances are not confined to the quantum world. They operate at macroscopic scales, where the relationships between forces govern the behavior of entire systems. Think of ocean waves as we did earlier. Wind provides the driving force. Water resistance is the opposing force, and gravity is the bounding force that creates the predictable rhythmic patterns we observe. These patterns are the result of non-local interactions across the system. Changes in one part of the ocean can affect wave patterns miles away. This idea scales up to even larger systems. In weather systems, for instance, a shift in atmospheric pressure on one side of the globe can lead to changes in wind and weather patterns on the other side. This interconnectedness, this non-local behavior, isn't mystical. It's a real physical feature of how large systems work. And it's these systemic connections that provide a more grounded, more observable version of Bohm's interconnected universe. So where does this leave Bohm's idea of the implicate and explicate orders? Is there still room for these concepts in our new, more holistic framework? Absolutely. Bohm's vision of reality as an unfolding from a deeper order remains powerful. It just needs to be reframed in terms of observable systems rather than quantum abstractions. Instead of thinking of the implicate order as a hidden, unmeasurable realm that exists only in the quantum world, we can think of it as the underlying system-level forces that govern the behavior of entire networks. These forces are implicate in the sense that they're not always visible at the surface, but they give rise to the explicate world we observe. Think of an ecosystem. The implicate order here could be the invisible forces that maintain the balance of the system, interactions between species, nutrient cycles, energy flows. These forces don't exist in isolation. They are part of the system's interconnected web, and the explicate order, the world we observe, is this outcome of these forces interacting. The species we see, the way they behave, the changes in population sizes over time. In this view, Bohm's implicate order isn't some mysterious hidden layer of reality accessible only through quantum theory. Instead, it's something we can study and observe by examining how systems behave. By understanding the forces that drive and balance these systems, we get a clearer picture of how interconnectedness works at all levels, from the smallest organisms to the largest cosmic structures. Now, This shift in perspective from a quantum interpretation to a systems-based interpretation doesn't just change how we think about reality. It also has real-world applications. Understanding interconnectedness at the level of systems helps us make sense of everything from climate change to healthcare to economics. For instance, in environmental science, we now know that ecosystems are delicately balanced webs of life. Biodiversity, the variety of species within an ecosystem, helps maintain the resilience of the system as a whole. Remove one species and you risk collapsing the entire network because every species is interconnected through complex relationships of energy and nutrient exchange. This is Bohm's vision of interconnectedness playing out in a real, observable way. Or consider global health. The spread of infectious diseases like COVID-19 has shown us just how interconnected our world is. A virus that emerges in one part of the globe can, through the invisible networks of travel and human interaction, spread across entire continents. In the world of economics, too, we see these interconnected forces at work. Financial markets are complex systems where the actions of one group can send ripple effects across the entire globe. A decision made in one country's economy can impact markets thousands of miles away. Again, a real-world example of non-locality and systemic interconnectedness. These are all cases where interconnectedness is not a theoretical construct, but a practical reality. By understanding the whole system and how its parts interact, we can better predict and respond to changes, whether they're environmental, social, or economic. Now that we've explored how interconnectedness works in holistic systems and reinterpreted Bohm's vision of reality, we've arrived at an exciting point in our journey, the realization that the interconnectedness of the universe is not some distant or abstract concept, but something we can observe, understand, and apply in practical real-world contexts. But what does this new understanding mean for us going forward? How can this expanded perspective of interconnectedness influence not only how we think, but also how we live, how we interact with the world, and how we address some of the most pressing challenges of our time? Let's delve into the profound implications of this new way of seeing reality, because this isn't just a philosophical exercise, it's a way of shifting our worldview, and that shift carries with it both responsibilities and opportunities. Understanding the world as a deeply interconnected whole can change the way we approach everything from our relationship with nature to our social structures and even our own inner lives. If we accept that everything is interconnected through the systems that govern life, matter, and energy, then we must also accept that our actions have far-reaching consequences. Whether we're talking about environmental systems, social structures, or even the complex global economy, understanding the ripple effects of our behavior becomes crucial. Think about climate change. For decades, we treated the environment as a separate entity, something we could extract from and exploit without thinking about the larger systems that sustain life on Earth. But now we know that our actions, our burning of fossil fuels, deforestation, and industrial farming, have altered the climate in profound ways. These changes ripple out through ecosystems, weather patterns, and even human health. We're witnessing the interconnectedness of the planet's systems in real time. The warming of the oceans affects marine life, which in turn impacts fisheries, economies, and food supplies. Melting glaciers lead to rising sea levels, displacing entire populations and transforming coastlines. This new understanding of reality carries with it a responsibility. We can no longer pretend that our actions exist in isolation or that the consequences of those actions are contained. The health of our planet, our societies, and our economies are inextricably linked. Every decision we make, whether as individuals, communities, or nations, feeds into a larger system. And this means that if we want to create a sustainable future, we have to start thinking systemically, understanding the interconnections, and acting with the awareness that our choices will impact not only the present but also future generations. This responsibility also extends to the social systems we inhabit. The pandemic has shown us just how deeply connected our global community is. A virus that emerged in one corner of the world spread rapidly through travel, commerce, and human interaction, demonstrating how interconnected our health systems, economies, and societies truly are. To address global challenges like pandemics, climate change, or poverty, we need to recognize that the solutions must be just as interconnected as the problems. Beyond our responsibility, embracing the interconnected nature of reality challenges us to rethink the very idea of progress. Traditionally, progress has often been viewed through a linear, individualistic lens. More wealth, more consumption, more technological advancement. But when we look at the world through a systems lens, we start to see that true progress isn't about endless growth or extraction. It's about balance, maintaining the health and stability of the systems that support life. In nature, we see countless examples of this principle. Ecosystems don't grow infinitely. They develop to a point of balance where resources are used and replenished in a sustainable cycle. Forests, for instance, maintain a delicate balance between the life they support and the resources they consume. Trees take in carbon dioxide and release oxygen, animals recycle nutrients, and the entire system operates in harmony. If one part of the system grows unchecked, it throws the entire balance out of order. Our current economic models, by contrast, often emphasize growth at all costs, but this approach ignores the fact that unchecked growth can destabilize systems, whether it's an ecosystem or an economy. As we continue to deplete natural resources, pollute the environment, and create massive inequalities, we risk destabilizing the very systems that sustain us. What if, instead of prioritizing growth, we prioritized resilience and sustainability? By focusing on balance, whether in our economies, our social structures, or our personal lives, we can build systems that are more adaptable, more resistant to shocks, and more supportive of long-term well-being. This isn't just about saving the planet, it's about creating a world where all people and systems can thrive. Let's turn now to our social systems, because interconnectedness doesn't just apply to ecosystems or economies. It also applies to human relationships. Understanding that we are all part of larger systems can fundamentally change the way we view ourselves and how we relate to one another. In many ways, modern society has pushed us toward individualism, the idea that we are separate, self-contained individuals responsible only for our own actions and primarily motivated by personal success or survival. This view of the world fragments us, creating artificial separations between me and you, between groups, nations, or ideologies. But if we embrace the idea of interconnectedness, we realize that these divisions are largely illusions. Just as an ecosystem thrives through collaboration and mutual support, human societies function best when we recognize our shared responsibilities and our mutual dependence. The health of the whole system depends on the well-being of all its parts. In other words, my well-being is tied to your well-being. Your health, your security, your happiness, all of these influence the collective health, security, and happiness of society. Consider issues like poverty or inequality. When parts of a system are neglected, the entire system suffers. If we don't address the underlying issues of inequality, whether they're economic, racial, or social, those imbalances ripple out into the broader system, creating instability and conflict. By focusing on the interconnected nature of our world, we can create policies and social structures that promote inclusion, equity, and justice, because we understand that a more balanced system benefits everyone. This idea also has profound implications for our personal relationships. The recognition that we are interconnected invites us to rethink how we engage with others. Instead of seeing relationships as transactions or competitions, we can begin to see them as opportunities for collaboration and mutual growth. Empathy, compassion, and cooperation become essential virtues in this interconnected world, not just because they're morally right, but because they contribute to the health and balance of the systems we inhabit. Ultimately, embracing the interconnectedness of reality isn't just a shift in how we understand systems, a shift in consciousness. It requires us to move beyond the illusion of separateness that has dominated much of Western thought and adopt a more holistic view of the self, the world, and the cosmos. This shift in consciousness brings us back to many of the ancient philosophical traditions we touched on at the beginning of our journey. The idea that we are not isolated beings, but are fundamentally connected to the universe, is at the heart of many wisdom traditions, from the oneness in Eastern spirituality to the idea of interdependence in indigenous cultures. These traditions understood from science that life thrives through balance, connection, and harmony today as we face complex global challenges, from climate change to inequality, from political polarization to mental health crises. We are called to realize this ancient understanding. We are not separate from nature nor one another. The choices we make, the actions we take, and the values we hold ripple out into the world we are part of. When we see ourselves as interconnected, we begin to live differently, more mindfully, more compassionately, and more consciously aware of our impact on the whole. So what can we take away from this interconnectedness? How do we apply this new understanding in our daily lives and in the larger systems we're part of? First, we need to cultivate a sense of systems thinking, the ability to see the connections between the parts and the whole. Whether you're thinking about your personal life, your community, your workplace, or the planet. How are these pieces connected? How do my actions impact the larger system? What can I do to promote balance, sustainability, and resilience in this system? Is going to bring a sense of global responsibility. In a world where everything is connected, what happens in one part of the world affects the entire system. Choices, from the food we eat to the products we buy, have global consequences. Conscious, sustainable choices, we can contribute to the health of the global ecosystem. Third, we must compassion and cooperation. In an interconnected world, competition and division only create imbalances. By working together, by fostering empathy and understanding, we strengthen the connections between us and build more harmonious societies. In closing, I want to leave you with this thought. Reality is not fragmented. It is not a collection of isolated parts. It is an interconnected whole, a vast living system in which every part is linked to every other. The ancient wisdom of our ancestors and the modern both point us toward this truth. And once we embrace it, it changes everything. It changes how we see the world and how we care for the planet. To live in the whole is to live with awareness, to recognize that everything is connected, and to act with that awareness in mind. As we move forward into an uncertain future, this understanding of interconnectedness may be the most powerful tool we have for creating a better world for each other and for the generations yet to come.